Okay, here is a hyperbola. A hyperbola is the set of all points in a plane where the difference between the distances of 2 points from two distinct points is a positive constant. Okay, this is similar to the definition of an ellipse. Obviously, two completely different graphs, but when we talked about an ellipse, we measured the distance from a point to each foci, and when we added it together, it was the same number. Here we're talking about a point and the distance to each foci, and we're subtracting them, and it is the same number. Okay, don't worry about the picture yet. Okay, we'll look at horizontal and vertical, and you can write the picture down then. Okay, what I want you to notice about the picture, you're going to think that it looks like two parabolas, right, going away from each other. Kind of looks like that. What we're going to have is we're going to have some asymptotes that those curves approach. Okay. So we're still going to have a center, we're going to have vertices, we're going to have foci, just like we did in an ellipse. Okay. And we identify these as vertical versus horizontal based on where the vertices and foci are from each other. Okay. What I first want to show you, though, is an illustration on this property where the distance from a point to the two foci, the difference is always going to be the same. Okay, what does that mean? So here, okay, the red is our hyperbola. Okay, you notice here's a point in purple. The distance from this point to the focus is measured here. The distance from the purple point to the other focus is measured here. And then their difference is there. Okay? Notice how, no matter where I move it, it stays as 3.51. Also, I have a point over here in orange. Okay? This distance, okay, in orange I have from the point to focus. Here, this distance points to focus, and their difference is over here. Notice how that is also 3.51. Okay, no matter where I move it. Okay, so that is what makes a hyperbola special. We take any point on that hyperbola, the distance measured to each foci, the difference will always be the same number. Okay. All right, let's talk about the standard form. Okay. First, we'll talk about horizontal, and then we will worry about vertical. Okay. So, our horizontal ellipse, or excuse me, hyperbola. What's different? This looks very similar to an ellipse equation, but what's different? There is subtraction in between, okay? That is how you tell it is a hyperbola, all right? Our center is still going to be at HK. Our foci are still going to be C away. Our vertices are still going to be A away from that center. Okay. There are going to be asymptotes. Okay. Now, you can write down this equation for the asymptote, but I'm going to show you how to look at your graph and write the equation without having to think about this formula, okay? What I want you to realize from the formula is that the slope of our asymptotes, okay, they're lines, the slope of these asymptotes, it's going to come from A and B, okay? these asymptotes also, if you notice, will pass through our center. Okay, so here are our asymptotes. They pass through the center. Okay. So what we will do, we will plot the center. We will plot our vertex points. Okay. We will plot our foci. Okay. Let's go ahead and write this down. Our C we find by taking C squared as A squared plus B squared. Please separate this from how we find C in an ellipse. Okay. In an ellipse, we take C squared as A squared minus B squared. In a hyperbola, we take C squared as A squared plus B squared. Okay. All right. So back to the graph. Okay, just like in an ellipse, we plot the center. We plot our vertices AOA. We plot our foci COA. This time, our foci are going to be farther away from our center than our vertices because they have to sit inside of the curve. Okay, so our C is going to be bigger than A. Now, do you notice how there's this rectangle here? Okay. What we're going to do is we're going to plot our vertices AOA. We're going to use B to plot points that aren't on our curve, but we're going to use them to help us very lightly. Here, I'll use B. We're going to plot these points very lightly like we would for an ellipse. And what we're going to do is we're going to make a rectangle using our vertices and those B values. What do you notice about our asymptotes in that rectangle? What? They're the diagonals. Okay, so if we can draw this box here, then we can draw our asymptotes through the diagonals. Okay, and that's how we're going to write those equations instead of trying to think about this formula up here. Okay. Any questions before we talk about vertical? Okay. Intuition, what do you think is going to change when we go to the vertical? Okay. I like the change of variables there. Okay. When we have a vertical, our y squared is positive. The x squared is the one that's being subtracted. Notice how A stays with the positive variable. Okay. A could be smaller than B here. That is not something that we need to look at. Okay. A and B could be the same. One could be bigger than the other. That does not matter. The A squared always has to be with a positive variable. Okay. So just like here, our center is HK, our foci are COA, but now vertically. Our vertices are AOA, but now vertically. A and B are still going to help us with the slope of our asymptotes. So we will plot the center. We will plot our vertices. We will plot our foci. Okay. We will take B and plot those points to make a frame, okay, or a rectangle, so that we can draw our asymptotes through those diagonals. Okay. The curve itself is actually going to be the last thing that we draw. we will do one example of each. Okay, and just like with parabolas and ellipses, it makes a lot more sense once we're doing it with actual numbers, right? Okay, questions before we move on? If it is not in standard form, we must get it there. We are going to start out with one in standard form. It's very basic, so we can kind of see the layout of how we're going to find everything. Okay? Are we ready? Everyone have what they need written down? Okay. Here we go. X squared over 9 minus y squared over 25 equals 1. Is this going to be a horizontal or vertical hyperbola? It's going to be horizontal. Also, we know it's a hyperbola because we have subtraction between the two squared terms. Okay? All right. So this is going to be horizontal because the x squared is positive. Okay, first thing, let's identify the center. 0, 0. Now let's identify A and B. Which one is A squared? Okay, A squared is always with a positive term. So A squared is 9, which means A is 3. B squared is 25, which means B is 5. All right? So since A is 3, and we have a horizontal hyperbola, I'm going to move out 3 from my center, and those are our vertices. So at 3, 0, and negative 3, 0. Okay. Let's go ahead and, since we're working with A squared and B squared, let's go ahead and plot our foci. How do we find C? C squared is A squared plus B squared. So C squared is 9 plus 25. What does that make C? 6. Radical 34. Right? Okay. Radical 34 is almost 6, not quite. So from our center, we're going to move out almost 6. And so our foci are at radical 34, 0, and negative radical 34, 0. Okay, now for the fun stuff. Okay, very, very lightly, let's plot those B points. Okay, so since B is 5, I'm going to go 5 away from the center and plot a really, really light point. Okay, if you're using a pencil, do this very lightly. Okay, then what I want you to do is make a rectangle with your A and B points. So very lightly, we're going to make a rectangle. Okay, this is not a part of your graph. It's just going to help us get the asymptotes. Okay, so I want you to do this very lightly. Now, we're going to actually draw our asymptotes in. Okay, our asymptotes are going to go through the center and the diagonals. Okay, so There are our asymptotes. Okay? And then what we'll do is let's go ahead and draw the curve since we're working on the graph. This is my vertex. We're going to draw our curve and it has to approach our asymptote. We just plot them. The foci just lie inside. Now let's talk about the equations to these lines. Okay? Let's talk about this one. What's our y-intercept? 0, right? What's our slope? We go up 5 and over 3 to get to that corner, right? So our asymptote y equals 5/3 x. What about this one? What's the slope here? Negative 5/3 x. Okay? Your slopes will always be just opposites. Okay? The rise over run will be the same. One will be positive, one will be negative. Okay? And all you have to do is look at, here we went up b and over a. Sometimes you may go up a over b depending on which way we're opening. All right? So just look at the rectangle that you drew. How far did we go up? How far did we go over to get to that corner? Questions? Okay. Let's take it up a notch. How do I know if this is a hyperbola? In this form, they're all going to be set equal to 0. What do we need to look for? It needs what kind of variables, first of all?
Both.
Okay. We need x squared and y squared. Okay, they have to be opposite signs. One's positive, one's negative. That is how we know that this is a hyperbola. Okay. So, we got to do some work here, don't we? We need our x minus h squared and our y minus k squared, so we need to complete the square 2 times with both variables. So, I'm going to keep my y's first, since that's the positive variable. All right, so I'm going to factor a 16 out of y squared, which means I also need to factor it out of 64y. 64y, correct? Yes? Okay. What is our coefficient for x squared? -1. So that -1 has to be factored out of the x squared, which means it also needs to be factored out of 2x, which would make it a -2x. Okay? So then we'll move our -47 to the right side. Oh, we'll subtract 47 over to be -47, and then we'll have to add our 2 mystery numbers. Okay? What completes the square here? 4, but what are we really adding? We're really adding 64. What completes the square here? 1, but what are we really adding? -1, so make sure you add a -1 to the right side. So what we have is 16 times y plus 2, the quantity squared, minus x minus 1, the quantity squared, equals 16. That is convenient, isn't it? Just like with an ellipse, this needs to equal 1. So to force it to be 1, we're going to have to do what? Divided by 16. So we have y plus 2, the quantity squared, over 1, minus x minus 1, the quantity squared over 16, equals 1. There is our standard form. Horizontal or vertical? Vertical because the y is positive. Where is our center? How about 1, negative 2? Be careful. I know that the x comes second, but we still have to pick the x first for our center. So 1, negative 2 is our center. Which one is a squared? A squared is 1, which means a is 1. B squared would then be 16. So b is 4. So what I'm going to do, since a is 1 and we have a vertical hyperbola, I'm going to move up 1 and down 1 from our center for our vertices. So our vertices are at 1, negative 1 and 1, negative 3. Let's go ahead and look at our foci before we get too much further. All right. C squared is a squared plus b squared. A squared plus b squared would be 17. Do you agree? So C is the square root of 17. Square root of 17 is a little bit over 4. So from our center, we're going to go 1, 2, 3, 4, just a tad bit over 4. So our foci, all right, we moved vertically. So we stayed at 1, and from negative 2, we went a positive radical 17 and a negative radical 17. Remember, I will let you write those points together if C is irrational. Now the real fun begins. Okay? We need our asymptote so we can draw in our curve. So since B is 4, I'm going to go B away horizontally, since this is a vertical hyperbola, and I'm going to plot points very lightly. And with my vertices and these 2 points, we're going to make a frame. How do we draw in our asymptotes? Through the diagonal. So center through the diagonal. If you want to use like your ID card to get these nice and straight, you can. Does not bother me if you don't. All right, and then what we can do is from our vertex points, we can make a curve that approaches our asymptotes. Okay? Now we have to write the equations of these asymptotes. Okay? I would like to remind you about point slope form. Does anybody remember what point slope form is? Absolutely not. If we have a slope and we know a point on the line, then we can write y minus the y value equals slope times x minus the x value. Does that seem vaguely familiar? Not at all? Write it down then. Those of you who go on to calculus, point slope form will be your best friend. Okay? I promise you, this is easier than setting y equals mx plus b up and solving for b. This is going to save you time and energy, and it will be less work. We all like that, right? So, what point does the asymptote, what point do your asymptotes go through? What? They are always going to go through the center. Your center is going to be the point. All right? So our center is 2, 1. What's the slope of this line? We go up 1 over 4. What's the slope? 1/4. So we're going to write y minus negative 2 equals our slope times x minus 1. What's the slope for this line? Negative 1/4. So y minus y equals slope times x minus x. Now, in the back of the book, they might move that negative, they might subtract that 2 over. I am fine with you leaving it like this. Y plus 2 equals 1/4 times the quantity x minus 1. Is that less work than doing the y equals mx plus b? Yes. Okay, so please write them in point slope form. Okay. Questions? Okay. Your homework here. Tomorrow we will be working backwards with hyperbolas. Don't forget our quiz is on Friday over all 3 of the conic sections we've talked about.